This video is for AP Stats, section 7.2. We're in means and variances of random variables, and I'm doing problem 7.46, and we'll do 7.47, and we'll talk about it, how to do it out of our AP Stats book. Both of these problems, you have to think about rules 1 for means and for variances. So rule 1, remember, talked about the mean of a transformation either went up by, as in was added or subtracted by whatever that value of a would be, or you multiply whatever the mean was by a constant b. So if the mean of a sample was, well, the mean of a random variable was 4, if you want to add 5 to that mean, the mean of the transformation of the random variable would be 9. If you want to multiply by 2, then it would be 8. 2 times, sorry, because it was 4, okay. With the variance, it's slightly different. We have to pull out something that we talked about in first semester. The variance of a linear transformation is just that constant squared times the variance of the random variable x. Remember from chapter 1 that whatever the a was for a mean matters because that would shift that whole distribution up. For a variance, shifting everything up doesn't change how far it's spread. So in here, when we're looking at variance of a random variable, whatever the a is doesn't matter because that's not going to change that variance. Remember, variance is resistant to change, or resistant to adding. Alright, so let's look closer at 7.46. It says Glass Act 1. In the process from manufacturing glassware, glass stems are sealed by heating them in a flame. The temperature of the flame varies a bit. Here's the distribution of X measured in degrees Celsius. I'm going to get that down real quick. Alright, so there's a distribution. We have 1, 2, 3, 4, 5 outcomes as the temperature and a probability for each of those. Looking at it briefly to make sure it's legitimate, I see 0.25 and 0.25 would be 0.5. That gives it to 0.8, 0.9, and 1, so that's good to go. They all add up to 1. And if we're going to find the mean of x, or mean of the temp, remember we just take those outcomes, multiply them by their probabilities. There's not a dividing step when you do a mean this way because the dividing that you would do is kind of already in the fact that these probabilities are ratios. So they kind of have the dividing built in. I'm going to pause this for a second and figure out what that answer was. Okay, that came out to 550 exactly when I did it. Remember the variance squared. I'm pulling this exactly out of the summary on page 426 if you needed to skip over and look, is you take that number, you take each outcome in the probability distribution, subtract it from the mean, square that, and then multiply by the probability. So like for the first one, we'll do 540 minus 550 squared times 0.1 plus 545 minus 550 squared times 0.25. I'm going to finish setting that up and then calculate it, and I'll see you back in a second. Okay, I've got all my outcomes of x inputted here. I've got my mean is 550 consistently across there. On this next step, I'm going to do the squaring, the subtraction and the squaring real quick, and then I'll after I pause it, I'll do the multiplying on. We'll just see what our variance is, which will then square root to get the standard deviation, which is what they asked for. Okay, I did this calculation here on the bottom of the screen, and I got the variance to be 32.5. When I go ahead and square root that, then the standard deviation is, come on, square root, where you at? 5.7, roughly. Okay, let's pause and go on number 2. The target temperature, or part B, the target temperature is 550 degrees. What are the mean and standard deviation of the number of degrees off target X minus 550? Another way of asking part B, where it says, where it's asking for the number of degrees off target X minus 550, is just how many degrees is the temperature in the distribution away from 550, and what's the average of that, of how far that is from the temperature, and what's the standard deviation of how far that is away from the temperature. So I'm going to build another chart here to go along with that. That first one of 540 is negative 10 degrees away from the target temp, right? And we're going to keep that 0.1. 545 is 5 degrees under. It's not right. Right at 5. There we go. With the probability of 0.25 that we just carried over from the original chart. The outcome 550 would be 0 degrees away, and that's 0.3. 555 would be 5 degrees over. Again, that's 0.25. And 560 would be 10 degrees over. Then we'll find this average. So the mean of X minus 550 will be negative 10 times 0.1 plus negative 5 times 0.25 plus 0 times 0.3 plus 5 times 0.25 plus 10 times 0.1. Forgot to fill it in earlier. When I calculate that out, what the average distance the temperature away from the target temp was 0. So then let's do the standard deviation from that, which means we need to do the variance from that first. So we'll do negative 10 minus 0, which is to be negative 10 squared, times 0.1 plus negative 5 minus 0 squared times the 0.25 plus 0 minus 0 squared times 0.3. That's going to be 0. I'm actually just going to skip that one for now. Plus 5 squared times 0.25 plus 10 squared times 0.1. That's 100 times 0.1 plus 25 times 0.25 plus, again, the 0 that we left in the middle, plus 25 times 0.25 plus 100 times 0.1. That's going to equal the variance of the number of degrees off target was 42.5, which we then square root to get the standard deviation. And when I do square root of 42.5, I get 6.52. So the standard deviation is 6.52 degrees away from that target, which I think is interesting. That's actually higher than just the standard deviation of the mean that we looked at on the last slide. Okay, part C. A manager asked for results given in degrees Fahrenheit. The conversion for X into degrees is this. You've probably done this in science class before. 9/5 X plus 32. If we're relating it back to our rules, that we looked at, this is similar to then the mean of ax plus by, or a plus bx equals a plus b mu of x, and the variance of a plus bx equals, remember, b squared times the variance of x. Remembering, as I said a couple minutes ago, that adding to a variance doesn't change anything. So if our mean is, let's go back, what was our mean? Our mean was 550, like we wanted. Then the mu of 9/5 x plus 32 will be 32, I wrote that backwards, so it would have been switched. 32 plus 9/5 times 550. I'll pause to calculate. I got 1,022 on that. And then sigma squared of 32 plus 9/5 x will be, I'm going to square the b that we had, multiply it by whatever our variance was. Let's get back and look at what that was. Our variance, remember, was 32.5. I need some more space. 9 over 5 squared would be 81 over 25 times 32.5. I'm still going to need a calculator, so let me pause. Okay, we got the variance of that Fahrenheit change to be 105. Remember, to get the standard deviation then, we need to square root that. Square root of 105.3. Square root of that is 10.26. Alright, so we've done part A, part B, part C. Now 747, they required you to do some simulation. In continuation of the previous exercise, describe the details of a simulation you could carry out to approximate the mean temperature and the standard deviation in degrees Celsius. Then carry out your simulation. Are the mean and standard deviation produced from your simulation close to the values you calculated in 746A? So really just what you need to do is set up your own distribution, your own simulation that follows the same probabilities that they gave us in that chart in 7.46. So here's 7.47, the simulation. Remember, in 7.46 we had probabilities of 0.1, 0.25, 0.3, 0.25, 0.1. And I've said always that when you have probabilities that you need to simulate, then you just are going to do random integer on your calculator, and we're going to do 1 to 100 because we have 100%.